In this, which is a rather long lecture, I shall describe a little bit about the radiation densities that we need to use in the processes for spectroscopy, and also the Einstein's semiclassical model as an introductory concept for macroscopic coefficients that can be measured. Now, the lecture has about 3 parts. The first part will contain a little bit on the radiation density, and let me recall from your elementary atomic physics or chemistry the Max Planck's formula, which revolutionized the whole of physics and led to the discovery of quantum mechanics later. Radiation interacts with matter, and it was first conceived by Albert Einstein through a semi-classical model by invoking 3 elementary processes, and these processes are known as absorption, spontaneous emission, and stimulated emission. So, let me explain that a little bit and also explain a bit on the Einstein's semiclassical model. First, let us look at the Planck's formula, and the object of interest for radiation density in Planck's formula is the idealized body known as a black body, which when it is heated to very high temperatures and is in thermal equilibrium with the radiation that gets emitted due to the heat, the black body emits all frequencies, radiation of all frequencies. The thermal equilibrium essentially means the radiation is inside the cavity and it is in equilibrium with the black body, and one measures the radiation density as a function of frequencies. One gets a distribution like this for a given temperature. If you write the radiation density as rho nu as a function of nu, the frequency, one typically gets a graph something like that for a given temperature T. Radiation density is distributed for various values of the frequency with different densities, but it also has a maximum frequency, that is, the density is maximum for a particular frequency at any given temperature. What one found was that if you plot this at various temperatures, for various temperatures of the black body, rho nu, one gets this for a T1, say let us call it T0, and another graph T1 where the maximum radiation density, that is the frequency for which the density is maximum, is greater if T1 is greater than T0, and likewise if the temperatures increase, the maximum shifts towards higher and higher frequencies. But please note that the radiation density is very low, or it is almost 0 for very low frequencies and also for very high frequencies, and therefore the black body emits radiation with frequencies which are in a rather limited range. Even though all frequencies are acceptable, what you see here is that low frequency radiation density approaches 0 and the high frequency radiation density also approaches 0, and therefore how do we obtain this graph? Max Planck was the first one who solved this riddle with his own formula, and he came up with the idea that the black body has atomic oscillators which get excited when the temperatures are increased, that is when it is heated, and the oscillators are in thermal equilibrium and they emit radiation, and the energy of the radiation that they emit is not arbitrary. The energy is proportional to the frequency, and a proportionality constant was introduced by Planck called the quantum of action, and it is a very small number, but it is a finite number. Therefore, the energy emitted by the black body is discrete. E is not all energies, but energy comes in the form of packets. This was the proposal that Planck came up with, and in this proposal, of course, he introduced the constant of action, which he called as the quantum of action. It is an action constant. In classical mechanics, action means very, very specific things, and Planck's constant has the dimension E. When you write h, this is 1 by time, and this is energy. Therefore, Planck introduced h as energy into time. Okay. The radiation density rho nu for any given frequency nu, Planck's proposal was to give this particular formula. He derived this formula with that assumption that the energy is emitted in a discontinuous fashion, and it is h nu cube by c cube, the speed of light, times 1 by e to the h nu by kt minus 1, okay, where nu is the frequency, c is the speed of light, and k is the Boltzmann constant. K, in honor of Ludwig Boltzmann, it is a Boltzmann's constant, and its value is of course very, very small, and very precisely these days, of course, these constants can be measured, and the value is approximately 1.38 into 10 to the minus 23 joules per Kelvin, and kT is thermal energy at any given temperature T, and h nu by kT is the factor which, when exponentiated, gives us the weight of the frequency nu to the radiation density rho nu. Okay. Now, if you look at this formula carefully, rho nu as 8 pi h nu cube by c cube. Of course, this factor is dimensionless because it is energy divided by energy, h nu by kt. Anyway, any exponential sign, etc., should have factors which are dimensionless. But here, if you look at the dimension of rho nu, it is h nu cube by c cube. So, let me write that as h nu, nu square by c cube. Dimensionally, it is energy, which you can write as joules, and the per second square, because nu square, and c cube is meter per second whole cube. Therefore, the dimension that you have for rho nu is energy time per volume, per volume. This is the radiation density formula, and it also is such that on both limits, when you take nu to be very large and nu to be very small, this formula leads to a value of rho nu going to 0 for nu going to 0, nu going to infinity. That is very large values. That is easy to check, because if you write the formula as 8 pi h nu cube by c cube, 1 by e to the h nu by kt minus 1. Please remember, this factor, when nu is very small, h nu is much less than kT for any t, and therefore this is approximately h nu by kT, because it is 1 plus x, it is an exponential x, so it is 1 plus x, etc., and this is the factor, and this nu of course cancels with that, and so the formula for rho nu is 8 pi nu square kT by c cube, which goes to 0 as nu goes to 0. Okay. Therefore, the lower end of the graph is reproduced by the Max Planck's formula when nu goes to 0. What about the higher value of nu? That is also easy to see, because when you write 1 by exponential h nu by kT minus 1, and if nu is very very large, so that h nu is much larger than kT, then this is approximately 1 by e to the h nu by kT, and the rho nu therefore becomes 8 pi h nu cube by c cube times e to the minus h nu by kT, and you see that the exponential goes to 0 faster than the nu cube rising as nu goes to infinity. Therefore, rho nu also goes to 0 as nu goes to infinity. This is an extremely important formula that Max Planck came up with for the blackbody radiation, and we shall use that radiation density formula that Max Planck used in the next item, namely after we describe the 3 processes of the interaction of radiation with matter, first proposed in detail by Einstein and also worked out with some basic chemical kinetics that we needed to look at. So let us look at those 3 processes. If you go back to the lecture, the 3 elementary processes that we want to look at are the absorption, spontaneous emission, and stimulated emission. Let us imagine molecular system that the energy levels of atoms are quantized was already known in 1916-17 when Einstein came up with this theory, quantized energy levels, because Niels Bohr had already studied the hydrogen atom spectra and came up with the quantization of the energies and so on. So therefore, let us assume for molecular system an isolated 2 energy levels, E0 and E1. We will only consider a 2-level system. I mean, a 3-level and multi-level systems are the slightly more complex, and to understand the basic physics, it is possible for us to restrict ourselves to the 2-level system, and radiation corresponding to the energy difference here, E1 minus E0 by h, if you put that as a frequency, so radiation of a frequency nu falling on the system. What are the 3 processes? So here are the 3 processes that we need to consider. The absorption process is when the radiation falls on molecular system, a larger number of them, N0, in the lower energy state and N1 in the higher energy state. When radiation falls on molecular system in the lower energy state, the molecule rises to the higher energy, it rises to the higher energy state through the process of radiation absorption. So it is a straightforward absorption process. The other process on the side is molecules which are already in the excited state by themselves spontaneously releasing the energy through radiation and coming down to the ground state. Whether there is radiation or not, this is a spontaneous emission for all the excited molecules. And you also know that when there are multiple energies for a molecular system at any given temperature, and when we attain thermal equilibrium, we know that molecules are not all in the lower energy state or all in the higher energy state, but they are distributed. And this distribution follows what is known as the Maxwell-Boltzmann distribution. Therefore, we assume that there are more molecules in the lower energy state, slightly less in the higher energy state. But when equilibrium is attained, the rate of energy absorption by the molecules due to radiation falling on it is equal to the rate of emission of the excited states of molecules reaching the ground state. The excited states can come down to the ground state by two processes. One is spontaneous emission, the other is the stimulated emission. That is, the radiation itself may stimulate the excited state to release its energy and come down to the ground state, if you call this as the lower energy state. But in that process, conservation of energy requires that two photons, radiation photons, are emitted. So those are indicated by the two arrows here, and the constants B 0 to 1 and B 1 to 0 and A 1 to 0, these are coefficients which connect the rates of change to the number of molecules and to the radiation density. We will see that in the next step in the kinetics. The processes are absorption in the presence of radiation, stimulated emission in the presence of radiation, and spontaneous emission in the presence or in the absence. It does not matter, the emission happens spontaneously, radiation does not have a role. So these three processes we can see, and also there are very elementary animations for that. So an absorption is essentially the molecule being raised to the higher energy state from the lower energy state due to absorption of energy from the radiation, and the spontaneous emission corresponds to molecule from the higher energy state by itself releasing the energy and reaching the ground state, and the stimulated emission is due to the presence of the radiation actually disturbing the excited state, and the molecule releases its energy, but in the process it releases two photons. So the idea of laser, the stimulated emission, light amplification through stimulated emission of radiation, was conceived by Einstein almost 40 years before lasers were actually discovered and experimentally set up. So these three processes can be used to study an elementary model for absorption versus emission. Let me pause for a break here, and then we will continue with the model for studying the thermal equilibrium in the presence of radiation through these three processes. Okay, so before we do this, we will again write to the three processes. This is energy E1, this is E0, and number of molecules in this state is N0, and the number here is N1. And the first thing that we know, thermal distribution N0 by N1, or let me write N1 by N0, the higher energy state by N0, is given by the Boltzmann distribution, namely E to the minus h nu 10 by kT. What is nu 10? That is this frequency, nu 10. So the ratio of the number of molecules in the excited state to the ground state is given by the Boltzmann formula. Shall keep that in mind. Now let us assume that this is all in equilibrium in the presence of radiation. So there is thermal equilibrium. So thermal equilibrium means that the rate of change of N0 due to absorption of radiation and its excitement to reach the level N1, E1, is the same as the rate of change of N1 to become N0. Therefore, let us calculate these two rates based on some phenomenological rate law. Usually we shall use the first order rate law. First order rate law is also what is followed by most natural processes, and here in thermal equilibrium, suppose we talk about N1 dN1 by dt, the rate of formation of N1 from N0, then that depends on N0 as well as on the radiation intensity or radiation density rho nu. Therefore, dN1 by dt is proportional to N naught, is proportional to the radiation density, and the proportionality constant is the rate coefficient, which we shall write B 0 to 1, process from 0 to 1, this is N1, N naught rho nu. Now, the rate of change of this is the rate of formation, it is positive. The rate of decay dN1 by dt minus is due to two processes, namely the stimulated emission and the spontaneous emission. These are two different physical processes, because in the stimulated emission there is radiation density. Here there is no radiation density. Therefore, minus dN1 by dt is, that is the rate of decay, is proportional to rho nu, is proportional to the number N1, and therefore it has also the phenomenological coefficient B 1 to 0 rho nu N1. This is stimulated, and the dN1 by dt spontaneous minus is to show that this is decay, is simply another constant A 1 to 0, but it is simply proportional to the number N1, because it is independent of the radiation density. So, the total rate is the sum of this and that, and this is the rate of change of N1 to N naught. Therefore, this is the same as the rate of formation of N1. So, if you equate these two, what you have is B 0 to 1 rho nu N0 is B 1 to 0 rho nu N1 plus A 1 to 0, that is the constant, the rate coefficient, times N1. This is thermal equilibrium. Now, just rearrange this a little bit and use the Maxwell-Boltzmann formula, namely we want to write N1 by N naught. So, let us write B 1 to 0 rho nu is equal to B 0 1 to 0 rho nu plus A 1 to 0 times N1 by N naught, and this is given by e to the minus h nu 10 by kt. So, if you do that, then we can write a formula for the radiation density rho nu as A 1 to 0 divided by B 0 to 1 e to the h nu 10 by kt minus B, this is 0 to 1, this is 1 to 0. This is just a rearrangement of this formula to give you this result. But remember Planck's formula for thermal radiation in equilibrium with the hot body which is excited, and that is actually 8 pi h nu cube. In this case the nu is the nu 10 by c cube times 1 by exponential h nu 10 by kt minus 1. So, this is Planck's formula, and these two formulas make sense, and they are equal only if you notice that this one, namely the B1 to 0 is equal to B0 to 1. It is also easy to visualize that the rate coefficient for the absorption of radiation and the rate coefficient for stimulated emission of radiation, which is that the state is in a higher energy and it's also being prompted by the radiation to reach the bottom. And it's possible to realize that microscopically these two processes will have the rate coefficient. It's a principle of detailed balance. One can verify, one can argue that these coefficients are the same, but the Planck's formula also tells us that unless these two are equal, it doesn't make sense. Therefore, if we assume that the absorption coefficient and the stimulated coefficient, stimulated emission coefficients, they are both equal, then we have an extremely simple formula. We have only one absorption coefficient, namely one B, a B and an A, and A is physically different because it is spontaneous emission, and you can see immediately the relation between A and B through this formula. First of all, what you see is that A, this is A by B times e to the h nu 10 by kT minus 1 is equal to 8 pi h nu 10 cube by c cube into 1 by e to the h nu 10 by kT minus 1, and this cancels out, this goes away, and therefore what you have is A, the spontaneous emission coefficient, is equal to 8 pi h nu 10 cube by c cube times B, which is the absorption coefficient. Thus, two macroscopically measurable coefficients have been introduced to study the process, and there is also a relation between them based on what is called a phenomenological approach, namely assuming a very elementary first order chemical kinetics rate processes. And the more important one is that not only that A and B are related, but B will be later shown by more accurate quantum mechanical theories as leading to the square of the dipole moment matrix element. I mean, we will see that later. Dipole moment matrix element between the two states E0 and E1. The absolute square of the dipole moment, and therefore a macroscopic coefficient will be directly proportional to a microscopic, that is a molecule parameter, the dipole moment, and thus establishes the connection between molecular properties and what you measure spectroscopically in an instrument using macroscopic coefficient. This was a proposal, and this has been verified at a linear level. We have used the linear law, namely the rate is proportional to the number, rate is proportional to the radiation density. These are linear relations. We have not used any other concepts. Therefore, in the limit of what is called low radiation densities and a reasonable degree of thermal equilibrium, these have been known and these are verified. We shall keep this in mind when we study the absorption coefficient using the dipole moment matrix element later, but this is a fundamentally important theoretical detail for understanding the first level, the linear spectroscopy. Let me stop at this point, and we shall see a little more about what is a dipole moment, what are polarizabilities, and what is the moment of inertia for a molecule in the next lecture. And that's important because the moment of inertia is generally known as a second rank tensor, and so is polarizability. The dipole moment in a molecule is a vector. Therefore, we need to introduce these concepts before we start using the matrix elements, before we start using the dipole moment squares and so on in the measurement of microwave, infrared and electronic spectroscopy. So the next lecture will introduce these three properties: polarizability, dipole moment, and moment of inertia. Until then, thank you very much.